fourth-year PhD student. Today I'll talk about synthesis, structure, and properties of ternary metal superhydrides. It's hydrogen-rich materials, and I work with such materials already 6 years, together with my colleagues from Jilin University, China, and Professor Katsuya Shimizu from Osaka University, Stan Tozer from Tallahassee, United States, and my colleagues from Russian Academy of Science, it's the Institute of Crystallography, Ivan Troyan and Igor Lubutin, and together with colleagues from Vladimir Kudalov Group in Lebedev Physical Institute, FIAN. Okay, it's quite big collaboration because the project is rather complex. Skoltech simply doesn't have enough equipment to study such materials, especially superconductors. Anyway, Skoltech is doing in this collaboration, this project, theoretical research and as well as experiment at low pressures. And even sometimes we can use the focused ion beam to prepare the diamonds. I will show what is that later. And high pressure diamond anvil cells is typically assembled in the Crystallography Institute of Russian Academy of Science by Ivan Troyan. They also perform a laser heating and synthesis of hydrogen-rich materials. Lebedev Physical Institute is responsible for transport measurements, electrical transport measurements, and superconductivity in this project. And the structural investigations we are trying to do in Russia, in Kysin, Kurchatov synchrotron, it's possible to work with low pressures. For high pressure, of course, we are mostly traveling to Europe or sending ourselves to Petra, ECRF, to France, to Spring 8 in Japan, to Shanghai, China, Sirius in Brazil, and Max 4 in Sweden. So we use different synchrotron sources in order to investigate structure of obtained compounds, obtained superhydrides. Okay, let me give you a short introduction about hydrogen-rich materials, which can be synthesized under pressure. Hydrogen actually, even at 0 GPa at normal conditions, can react with many metals and non-metals. The temperature of reaction is typically something like 500, maybe 1000 kelvins. And with alkali metals and alkali earth metals such as lithium, sodium, potassium, magnesium, calcium, hydrogen forms ionic lower hydrides. With yttrium, lanthanum, and lanthanoids, it forms 3 hydrides such as lanthanum H3, cerium H3, and it's almost maximum content of hydrogen in the metallic, say in the metallic part of periodic system. The most important hydride is CH4. It's methane. It's very stable compound with the highest maximum hydrogen content. Its composition of atoms is 1 to 4. And among metals, the maximum hydrogen content is in thorium-4H15. It's also superconductor, but low temperature. TC is about close to 8 kelvins. But anyway, hydrogen content is also close to 4. Okay, let's see now what will happen if we increase pressure of hydrogen. Which compounds we can get, which compounds we can obtain. So under high pressure, about 1 million atmosphere, we can get, if we increase concentration of hydrogen compounds, we can get first a family of tetrahydrides. It's a tetragonal compound such as praseodymium H4, praseodymium H4, calcium H4, neodymium H4. When we increase pressure of hydrogen, amount of hydrogen, we can get hexahydrides such as yttrium H6, europium H6, lithium H6, and even our recent work, we can get strontium H6, assemble atoms of hydrogen, molecules of hydrogen together in the unit cell with strontium atoms. They will interact and form such molecular compound. It's a semiconductor, yellow color semiconductor, which was described in our recent publication in 2021. Okay, if we continue increase pressure, we will get monohydrides such as neodymium H9, praseodymium H9, cerium H9. And after that, the most important class of superhydrides, it's a high temperature superconductors. It's a decahydrides, such as lanthanum H10, it's a cubic compound, thorium H10, and proposed yttrium H10, and so on. Of course, we can increase, continue increase the pressure and increase the concentration of hydrogen, content of hydrogen in the unit cell of compounds, and the final result, I mean, there may be the richest compound that was synthesized at this moment is strontium H22 by our group, synthesized by our group. Okay, I need to say that under pressure, it's very important factor is volume, because the compounds prefer to crystallize, these superhydrides prefer to crystallize in the closed packed hexagonal and cubic lattices. So almost all superhydrides are cubic or hexagonal, and quite rare to find the compounds with tetragonal lattice or with low symmetry lattice like neodymium H7. But typically, they are closed packed structures, because under high pressure, it's important to occupy position with the maximum density. And atoms try to form the crystals with maximum density. So at this moment, about 14 binary metal hydrogen systems were investigated under high pressure, and a lot of unique, interesting, unusual compounds, unusual hydrides were synthesized, such as molecular polyhydrides of lithium, sodium, strontium, iron, metallic polyhydrides of lanthanum, yttrium, uranium, thorium, cerium, barium, and calcium, and magnetic metallic hydrides, which demonstrate magnetic properties, should demonstrate according to theoretical calculation. It's a praseodymium H9, neodymium H9, and europium H9. So those 14 binary metal hydrogen systems. You can see it on the this slide, on this figure. In this figure, I just filled some squares in the green or red color to show how many elements, how many binary systems were already investigated. And among them, there are about 10 high temperature superconductors. It's hydrides of cerium, thorium, sulfur, calcium, yttrium, lanthanum, and recently two new superconductors were synthesized. It is hydride, tin hydride, tin H4, and yttrium hydride, yttrium H4. It's interesting to note that yttrium H3, which exists and stable at normal conditions, it is not superconductor. But when we add one hydrogen atom, it becomes a superconductor, high temperature superconductor with Tc higher than many cuprates. So it's just one atom of hydrogen changes completely the situation and completely changes the properties of this compound. It makes it very unusual, very outstanding. After intensive calculations and experimental work, we clarified the distribution of superconductivity in binary hydrides, and it was found that actually distribution in the periodic system and periodic table is quite simple. Almost all high temperature superconductors belong to so-called superconductivity belt. It's a series of elements with D0, D1, and D2 electrons on the outer shell. So all other elements actually do not form superhydrides, or if they form superhydrides, the superhydrides are magnetic. So it excludes superconductivity, and all superconductors, all high temperature superconductors among polyhydrides, they are located exactly in this superconducting belt among D0, D1, and D2 elements. It's interesting to note that this belt exactly coincides with the maximum of hydrogen content among the lower hydrides, which can be synthesized at zero at normal conditions, at atmospheric pressure. And it's very interesting because we can somehow extrapolate the data obtained at low pressure, at normal conditions, to the region of high pressures. Okay, let me say now a couple of words about experiments. as I told them, mainly we are working outside of Russia because our samples under high pressure is typically quite small samples. It's a micron size of samples. It's a microsynthesis. And we always need to use asynchrotron sources of radiation to clarify the crystal structure of compounds. So it's mostly studies abroad Russia, because Russia just doesn't have the good synchrotron resources. Okay, the first I will explain how the main instrument in high pressure science, it's a diamond anvil cell, works. So it consists of several parts. Okay, let's assemble it together. The part which rotates, it's called a gasket. It's a metallic plate which is about 300 microns, has a thickness about 300 microns. Typically it's rhenium. And after that, we should press this metallic gasket by 2 diamond anvils. It's a diamonds, cone-shaped diamonds with the plain top, which is called culet. And the culet size is about 100 micron, or say from 50 to 100 micron. And they press the gasket. And we need to glue these diamonds to the seeds. It's a special, special plate from tungsten carbide, and this plate is also glued to the piston and the cylinder which form the diamond anvil cell. So we can tighten this cell using the screws, and when we increase the pressure on the piston, this pressure transfer to the seeds, and after that transfer to the diamond, and after that transfer to the sample. So that's a way how we can create a high pressure in our cell, in our sample, and synthesize something and investigate behavior of matter under pressure. Okay, the second step of preparation is to deposit the electrical leads, electrodes on the diamonds, and prepare the high pressure chamber where we can place a sample and hydrogen pressure transmitting media or hydrogen rich compound like precursor such as ammonia boron, NH3, BORH3, and after that synthesized from these materials the hydride that we need. Okay, the next procedure is cutting gasket. So you see on the video how the ultraviolet laser actually makes some kind of channel in thin ceramic gasket, which consists of calcium fluoride in this case. And the thickness of this gasket is about 10 micron. So it's very precise work. Yeah, and step by step, we made this channel deeper and deeper, and finally we cut it some kind of hole for the high pressure chamber where we can place our sample. So it's shown on the right picture, it's shown in the yellow. So now the process is finished, and we can go to the next stage of preparation. And the next stage is to preparing the electrical lead. Possible to do using lithography or just deposition through the mask, through the physical mask. Okay, so on the next series of pictures, you can see the sample already heated. So this is exactly the polyhydrides already synthesized. It's a black material. The property is absolutely similar as a metal. And this is diamond anvil and the culet. As I said, it's a plain top place of the cone-shaped diamond, where exactly the chemical synthesis will go on. And this is the diamond anvil cells already prepared, compressed, and ready for experiments. So the last step is chemical synthesis. So we already placed the metallic sample inside of the chamber, high pressure chamber, reached the certain pressure that we want to use. And after that, we need to start doing the heating. Yes, so this is the process of heating. We need to heat the sample to temperature of several thousands of kelvins and decompose ammonia boron, which is a common source of hydrogen. The high temperature will decompose to hydrogen, and hydrogen immediately reacts with the metal. So this is a typical procedure how we how we synthesize our polyhydrides, our superconductors. We even did some COMSOL modeling of this process of laser heating, and you can see how the temperature rises during the laser pulse. It's milliseconds, from milliseconds to microseconds pulse. The temperature can reach even 4,000 kelvins. The main problem during the heating is that the diamond itself has very high thermal conductivity, and if the metallic sample is connected with that diamond, it cannot be heated. So we need to prepare some kind of sandwich. Firstly, it's an insulating layer, like ammonia boring. After that, metal particle, and after that, next insulating layer. It will be sandwich, and in this case, the metal particle will be isolated from the diamond and can be heated to so high temperature, so the synthesis will be successful. Okay. Modern industry of high pressure research. Actually, in order to do such experiments, you need to purchase diamonds. You need to find diamonds, and in Russia, there is an institute in Troitsk. It's called CEST, and this institute actually produced the diamonds and diamond anvils, and we can order it, and they already polished. Anyway, in each experiment, you need to polish it by yourself. So it's wonderful to have in the laboratory a polisher for diamonds, for such for diamond anvils actually. The next stage is you need to find a factory which will produce diamond anvil cells. Exactly, the metallic part, the piston and cylinder of diamond anvil cells. It's a very complex process, and we ordered it in Fab Lab, Skoltech, about 1 year ago, to produce several cells, and the quality was not so good. So we decided not work with Fab Lab Skoltech anymore, and it's really better to purchase such cells, but they are quite expensive. Each cell costs about 5,000 euro. Of course, you need to also have a microscope, good microscopes to work with micron size samples and gaskets and diamonds, quite small. All details, all parts of this system is quite small. And the next step, of course, is laser heating. You need to have quite powerful infrared laser and infrared optics. As I know in the Skoltech, I know only one place where such optics exist. It's a lab of Pavlos Lagudakis. Unfortunately, they do not have powerful lasers to do the chemical synthesis at high pressure in diamond anvil cells. Thin film sputtering and lithography is also necessary. And cryomagnetic transport measurements, we ask to do these measurements in LPI, the people from LPI, because they are really professionals in such field. And the Raman measurements can be done in Skoltech. In the Red Building, we have quite good instrument. It's a Hariba, and actually, I think it's good enough to work with any pressure up to several million atmosphere, several millions atmosphere. Powder X-ray diffraction mostly in this project, within this project, diffraction was done abroad of Russia using European synchrotron sources such as ECRF and Petra. And recently we started to use the pulsed magnetic fields because hydride superconductors, it's a high temperature superconductors, and they have quite high upper critical magnetic field. So you cannot suppress superconductivity without using pulsed magnetic fields. Pulsed magnets do not exist in Russia. In order to use the pulsed magnets, you need to go to other countries such as Germany. And we worked in 2021, we worked about 1 month to study our samples in Dresden, Germany. So let me say some words about applications. The main application of superhydrides is superconductivity, of course, using it as a superconductors. Superconductivity is a phenomena when the material loses its its electrical resistance at certain temperature, which is called a critical temperature. So below, when it's cooled below the critical temperature, there is no electrical resistance of such materials, and they can be used to conduct electricity with very high density of current. So you can create the magnets with extremely high magnetic induction, and they will not use any energy, they will not dissipate energy. So the main characteristics of all superconductors is its critical temperature, Tc, and the second important characteristic is critical magnetic field, upper critical magnetic field. If we apply external magnetic field, which is higher than critical upper critical magnetic field of material, it means that superconductivity will be completely suppressed, and it will disappear, and the resistance will be like a normal metal. So let's look at the parameters. You saw here the parameter of mercury. The Tc of mercury is about 4 kelvins. It was the first superconductor discovered. And we can look at the now the materials that we discovered here in Moscow. It's ternary hydrides, lanthanum, yttrium ternary hydrides. The composition is lanthanum, yttrium H10, so XH10 group. It's a cubic compounds with FM3M structure and IM3M structure for hexahydrides. And you can see that actually the electrical resistance, all of these diagrams, it's they are about dependence of electrical resistance on temperature. And you see that at certain temperature, about 250 kelvins, resistance suddenly drop and disappears. So change in electrical resistance about 1,000 from 1,000 to 10,000 times. Transition can be very narrow, about several degrees. Here it's a bit longer, a bit wider. And in the magnetic field, you see the transition actually shifts to the left side according to the normal behavior of superconductors. When we apply external magnetic field, it suppresses superconductivity, and it occurs at lower temperature that it should be without magnetic field. So the upper critical magnetic field can be estimated using the different extrapolation models. And for superhydrides, for polyhydrides, it's typically above 100 Tesla. It's a very strong magnetic fields which cannot be created using standard technology, some coils. It can be created only for short time in a very small space using the pulsed magnets. We also investigated the structure using synchrotron sources. We investigated the crystal structure of these hydrides, and we found that crystal structure is pretty simple. Actually, it's just cubic sublattice of metal, where the lanthanum and yttrium are randomly mixed. So there is no order, and the lanthanum and yttrium can replace any position in this crystal. And we also have very high symmetry cubic sublattice of hydrogen. It's an atomic sublattice, which exactly responsible for high temperature superconducting properties of those materials. Okay, and it's interesting to note that for other hydrides, the situation is similar. For instance, for lanthanum neodymium hydrides, lanthanum and neodymium also do not occupy certain positions. They are mixed, and actually it can be described as a solid solution of lanthanum and neodymium in metal sublattice. Okay, finally, I would like to show something about the pulsed magnetic fields. It's important investigation now. So we used pulsed magnetic fields in Rossendorf in Dresden, Germany in October 2021. It's a complex system. The magnet you cannot see, it's underground, and it has very narrow place channel to put their diamond anvil cell with the sample. And after that, it should be cooled to a liquid nitrogen temperature. And we control the temperature of the sample by flow of helium. You see here the some vacuum and the helium tubes. Experiment is now completely automated. We can control experiment from the control room because of safety reasons. And you can see the some cards that we obtain. Yeah, on the video, I'm now just extracting the sample, taking the sample away from the variable temperature inside. And soon we will see the diamond anvil cell which contains this superhydride. Okay, and this is, yes. So this is diamond anvil cells, and in the center of the cell, you can see the sample. So teeth with diamonds, and between them, the gasket is squeezed, and inside there is a small, tiny sample, about 30 microns diameter. Yeah, and the doors in this laboratory is very heavy and thick. It's because of safety reasons, again, to avoid any risk for staff, for people who work there because of possible explosion of the pulse magnets, because power is negative and just milliseconds. It's a duration of pulse. It's hundreds of milliseconds, so it's extremely high power. Okay, this is two pictures of typical results that we can get in this laboratory in Dresden. We could reach magnetic fields experimentally. We could reach about 65 Tesla in pulse. It's a very high magnetic field, almost maximum for diamond anvil cells. Extrapolated data, I showed a couple of circles for extrapolated data. It's up to 75 Tesla approximately. We saw that, so this curve is called magnetic phase diagram. For superconductors, we see that this is pretty linear. Characteristics is a little bit unusual. Not all superconductors can demonstrate such linear behavior in a strong magnetic field. So it depends on critical temperature of superconductivity on magnetic field. And on the left side, you can see the actually original data. It's a resistance of sample versus a magnetic field applied. Okay. And so finally, I would like to underline several conclusions. So polyhydrides have very high TC. It's a new class of superconducting materials, which has much better characteristics than all other superconductors discovered for last 100 years. Polyhydrides have a TC up to 250 kelvins now, and the critical magnetic fields is above 120, 160 Tesla. So we cannot destroy superconductivity. We cannot suppress superconductivity using the magnetic fields available on Earth. And they also have very high critical density of current. So it's very interesting because it means that they can be used to conduct electricity with extremely high density, higher than all known materials. And they can be used also as a sensors or electronic elements even now in diamond anvil cells, because there are optical windows and we can send the signals and some useful signal and detect the response, electrical response using the electrical leads deposited on diamond anvils. So now almost everyone can have their own superconductors. In my home freezer, I have such diamond anvil cell which has a superconductor which goes to superconducting state at about -27 Celsius. There are also several problems of hydride superconductivity, problems of this field. Unfortunately, because of samples are not very available for modern instruments, it's quite complex to investigate the key parameters of superconducting state. It's important to investigate, will be important for our future work to measure the superconducting gap, the energy of pairing of Cooper pairs, and heat capacity, London penetration depth, density of states, Eliashberg function, and electron phonon interaction strength. So this is our plan. This is our plan for future. So I think it's, I would like to stop at this point. I think I finished my presentation. I said all that I planned to say. So thank you very much for your attention.
Thank you, Dmitry, for very